Welcome to the 10th video in the Beginning Artificial Intelligence series. This video is going to tie the last video on evolution algorithms back to neural networks and Keras. I've already explained the code for the hyperparameter tuner in the last video, so let's just go look at an example of using hyperparameter tuner to make a model of Keras. I begin by allowing growth on my GPU. If you're not using a GPU, you will want to comment this out or delete it, but if you're using a CPU, I'd recommend not even doing this because it will take a really long time. So instead, I would recommend using Google Colab, which will allow you to use a Tesla K80 for free. I then import a dataset using Keras. This is all code taken from the Keras introduction video. Then I start the hyperparameter tuner. The way you do this is for each parameter you want, you assign it a variable, and it depends on how you want the parameter to be selected. So for this one, we have a uniform distribution. So it'll pick anything from 1 to 4 and anything between there. And the next three, we have a list, which will be used for the convolution filters, which you can see right here, or in each convolution filter. And it will select one of the elements here. And then for units 1, that's the same thing, but it will be passed to a dense layer right here. Then we adjust the learning rate and the batch size with a list 2. Now the volatility here stands for how often the mutation should occur. We don't actually want to mutate the learning rate and batch size that often, but we definitely want to mess with the architecture. So that's why these values are a little higher than these two. And then I enable integer here because we only want 1, 2, 3, or 4, or 3 I guess is the max. Actually, no, yeah, it will be 4. But we only are messing with 2, so we can actually change this to 3, because we actually only have to have 3 layers max. So 1 layer there, 2 layers there, and 3 layers there. And then this fourth one has to happen pretty much. I'm not giving it a statement for that. Okay, so before we actually get into hyperparameter tuner, I also wanted to go over just how I normally choose my parameters. Doing this with the hyperparameter tuner can take an extremely long time, so it's nice to just be able to guess and hope they work yourself. So the way most people do it is we always use things to the power of 2, so 2, 4, 8, 16, 32, 64, 128, and all that. There's no real reason for it, it just makes it simpler so that you don't have to adjust every single number. And so it makes it a little simpler just adjusting the combinations, because it doesn't really matter. 16 and 17 shouldn't really change much if we have like 16 or 17 units, but doubling that should make a difference. So that's why we kind of do that. For learning rate, we normally just do it to powers of 10, so 0.1, 0.01, 0.001, and etc. For batch sizes, we also do it to powers of 2, so 2, 4, 8, 16, etc. And for other parameters, you can see for like these two parameters right here, momentum should be 0.99 or 0.999. Epsilon should be as low as you can get it. We can actually just make this probably even lower, but I'll just keep it for now. We don't actually have to. We could make a hyperparameter for tuning this, but these values are all fine. Another thing you can choose is your activation function. The rectified linear unit is pretty much the best. Sometimes you can use sigmoids, but those are slower, and sometimes will make the gradient vanish, so that's not good. So rectified linear units are pretty much the best, and the only thing you would actually want to change for that is for the output, depending on what you want. Loss wise, you just pick what actually goes with it. So if you're using a softmax, that's pretty much a categorical cross entropy. You could use a mean squared error or something else, but this is pretty much the best option. If you're using a sigmoid, you could use a binary cross entropy. And if you're using anything else like a linear or a rectified linear unit, or anything that can actually give you higher values than like values between -1 and 1, anything outside of that, you'll probably want to use a mean squared error, sometimes an mean absolute error, depending on your circumstances. And that's pretty much for loss. Metrics wise, if you're using any type of classification, you just can put accuracy. If you're using something with linear values, or if you're doing a regression problem, accuracy is not the best metric. So that's just a little thing over all the parameters real quick. But this hyperparameter tuner is supposed to remove all that. It is nice to be able to just give them values like this, so you're not just giving it a uniform from like 1 to 100 or something. And so that's all of this stuff here. You can see then once we actually call the tune, this is going to be generations. This is the population, and this is the selection size. And then we pass the evaluation function here. And then we can enable verbose if we want. It's by default disabled. If we were to actually go look at the code and evolution algorithm here, we can see that it is disabled. We also can give it a crossover function and tell if the lowest is best, which we did go over this a little bit in the last video. Okay, now when we are done tuning, I print out the values, and for my last tuning, I got these values. This pretty much means, if we look, we have one layer, so we're not using these two layers, so we're only using this layer and these layers here. This layer is 32, and the dense layer is 32, because we're skipping these layers, so those don't matter. So 32 here, and then the learning rate is 0.001, and the batch size is 64. Now it's important to keep in mind these are actually pretty low values. If we wanted to really find the best, we would want to have this probably 100, so 100, the population size of 100, and then have this probably 100 generations, and then you could actually increase the selection size to like 10 or even 25 if you wanted to. The reason why I did not do that is it would take a really long time. My last test I ran, which we can actually view right here, I had the 10 generations with the population size of 10 and the selection size of 3, and it took more than 20 minutes. So they can take a while, especially if you have a bigger model or so. So this is a pretty small model, and we even decreased the size of the data set. So you can see this takes a really long time. You might even want to leave it overnight or something if you really wanted to find those good parameters. So I do not actually use this in a lot of my projects, mainly because of having to leave it on all night or something. That can take a long time. So I just normally adjust them myself. I pick values with like the 32, and you can also follow some other things. A common thing for convolution layers are if you have a filter size here and a stride of 2, you actually want to increase the next one. So if we have 32 here, because we have that stride there, we would put like 64 there, and then another stride, so 128 here for this stride, and so we increase like that. Of course, the genetic algorithm does not think like that. It just does random stuff and tries to find the best value. And you can also see the fitness value we are giving it here actually takes into account the validation loss. You wouldn't necessarily want to do this if you wanted to only use your loss, but because I wanted to actually learn the best validation as well for the parameters, I did validation, because there's certain parameters like batch size, which if you do lower may take a little longer to train, but it will make the validation better. So that's the reason why I do that here, and you can see I take the average of that there. And I also print these values out just so I can see them. So like you can see when I was doing it, I wanted to see what it was actually doing. And you can view at the very beginning here, we were getting an error of like 0.2. That was pretty low, even 0.8. But at the very end here, we got nothing near 0.8 at all, 0.1s and a 0.3. That's pretty much it. You can see the validation was not doing that good. Even the solution we got was, I think this one right here. This was the best one it gave us. And so the validation wasn't doing that well, but it did learn what was good for the loss. And you can adjust these values here for, right here, to make sure it has more mutations. You can see how the batch size in this actually did not change much. A lot of the times it was 64, sometimes 16, and we had a 32 and a bunch of 32s here, but it doesn't adjust that much. So if we wanted it to adjust a bunch, we could, but I didn't want it to adjust that much. And it's kind of funny. We do have a hyperparameter tuner, but it takes all these hyperparameters as well. So it's important to not stress about these ones much. I would just say anything less than 0.5 is probably good. because you don't want it. You want to get, so if you have a good solution, let's say you have a random mutation that you get a good solution, you don't want to lose that solution in the next generation. So by having lower values, you have the higher chance of keeping a good solution, but you also lower your chance of getting a different solution. So that's kind of how you can think of it for that. Alright, so this is the end of the video. In the next few videos, we are going to look at unsupervised learning, which means the labels for the X data are not used.